Hi, and welcome to 11.4. This is the notes for points of inflection and intervals of concavity. So a good amount to introduce you guys to here in the beginning. Um, the first couple of things here would be the vocabulary, right? And the vocabulary we see is this inflection, and it's going to be points of inflection, right? So I'll underline all that. And then concavity. Now, concavity you might have heard before. We are going to see today, and I'll describe it through. Um, there's a couple ways you can show it, and the method we're going to use to do so to find the points of inflection and the concavity of our functions. But what I will say is it's going to be determined within the second derivative of our functions. Okay, now we've only seen the first derivative of our functions, right? So we're going to be seeing the second derivative of our functions. And I do want to go into that. So if you have space or a note sheet next to you or something, whatever you want to do, I do suggest writing all this stuff down, this next part about second derivative. And then I'm going to show you a visual in relation to what our inflection points and our concavity and where we can notice them on our graphs. So let's go into the notation of just the second derivative, okay? And our notation for the second derivative is just going to be f double prime of x, okay? So double prime instead of just one prime, right? So, and that makes sense. And then we're also going to write it as d squared y over dx squared, okay? So those are our two notations here that we're going to be writing and using throughout today. Again, remember, this is when we just see the function as y equals something, okay? And let's just do a quick second derivative example, too. So example, let's do f of x equals 4x to the third. Well, first we have to take the first derivative, okay? So that would be 4 times 3, which is 12, x, and then n minus 1 is 2, okay? And then our second derivative, we just use the power rule again, just like normal, just like our first derivative. So 12 times 2 is just 24, and then x, right? 2 minus 1, n minus 1 is just 1. We don't need to write the 1th power. So this would be our second derivative, okay? And if you want to practice another one, I'll just write another one here. Example, just do f of x equals 5x to the fourth or something. And just try that one out. Pause it here if you want, and get that second derivative. Now, what I do want to show is the graph of the second derivative. So let's get into this. This is going to be the graph of the second derivative, and I'm just going to draw some arbitrary function here. Let's go with that, okay? And it doesn't really matter here. What I want to do here, though, is just show you how the inflection point, or the POI, we're going to call it, point of inflection, right? And then how concave up and concave down appear in the function as well. So what I want to introduce here is the shape of the function. Now, the shape has a lot to do with it, right? And I will say this section of our function here is facing down, okay? And we usually see this in parabolas, right? It's facing down, okay? And that means it's concave down, okay? And so that's what visually the shape would look like of the function here. Now, likewise, if our function is facing up like this, right? There's this it's opening up. We say it's concave up, okay? And I just wanted to throw that in there. So make sure you write that where the direction is really taking hold of what the concavity of the function is within intervals, okay? And when I'm talking about intervals, I'm talking about there are intervals to the concavity of a function, okay? So in the intervals I'm going to be talking about here, showing you, involve the inflection point, okay? So this is where the inflection point is now going to come into play in this visual. So the interval of the function being concave down is this interval, right? We're just looking at that section of the function. And where the function changes from concave down to concave up, let's just say it's right about here, and I'm going to draw it in purple, okay? That point, at that point where it flips from concave down to concave up is our point of inflection. Okay, so I'm going to draw just an arrow here, and I'm going to drag this part over, just so we're labeling this visual. That's a point of inflection. Now, looking at the rest of the function, there's actually another point of inflection here, and it's right there. Okay, right? It's switching from concave up to concave down. So that's another point of inflection. Okay, and so what we're going to be doing is identifying at what interval it's concave down, right? So this interval, and where it's concave up, okay, this interval, right, inflection point to inflection point. And then in this example that I drew, there is another interval here, right? It'd be this interval. But that's what we're going to be looking at today and figuring out. So hopefully that visual helps you out here. And let's move on now to an actual problem, number one. And what I did do over here on the right is write out exactly the steps we're going to be doing. Okay, so maybe write these too, because these are going to help you too, and you can always fall back on these to help you through this problem. Now, let's go to one. Now, the first step in these is going to be finding that second derivative. So that whole first part I spent time doing. That's what we're going to be doing first. We're going to find the first derivative or the second derivative of this function. So since we have y, our notation here has to be dy first. We're going to find the first derivative first, right? So dy dx is going to be, well, we're bringing down that 2, so we have 2 over 2. Well, that's just x, okay? And then we have the derivative of 2x, which is just 2. Okay, now let's get that new notation in here, the second derivative, d squared y dx squared, and this is just going to be 1. Now, our next step is to do exactly what we did when finding if the function is increasing or decreasing, which is finding where our second derivative is 0 and undefined. Now, here, it's definitely not going to be undefined, and it's also not going to be 0 either. What we have here, just for a quick sketch, is just a normal parabola, right? We have a x squared power here, so we just have a normal parabola, which means we only really have one interval, okay? And it means there's no inflection point. Okay, so we kind of lucked out here on number 1. There's no inflection point, and we only have one interval, right? Because those inflection points are what determining our interval. So in this step 2, determine the concavity, well, we don't have to plug in values into our second derivative here. And that's what it says in step 2, plug in values to the left and the right of your inflection points into the second derivative. Well, here, since there's no inflection point, we don't have to do this step. But what I will say, we do have to determine the concavity of this parabola. Well, it is definitely concave up, right? It's facing up. Another way we write it is the second derivative is greater than 0 here. So what I'm looking at here, there's two cases really that will only pop up. And in this case, we have this case B, and the second derivative is greater than 0, right? 1 is greater than 0 here. So what we want to write then for our final answer, and this is my third step that I have written out here, is write the concavity in interval notation. We're going to write that there's no inflection points. So POI is just none, or NA, whatever you want to write, not applicable. And then our interval notation, well, it's concave up, okay? And within the interval of, guess what? Since this parabola goes negative infinity to positive infinity, our concavity is going to be the same. So negative infinity to positive infinity. Okay? And that's just number one. We're done here. This is what we'll box as our answer. And I will say, when we get into number two, you're going to notice right away, it's not a power of two. It's not a parabola here. We're going to have to do a little more of these steps to determine the concavity. So let's get into it. And it's going to be fun here. So buckle up. Our first steps here, again, is find the second derivative. So let's do that. Notice my notation here, right? I have the first derivative notation and the second derivative notation. That's the money maker right here. We need that second derivative. Now, my steps say for the inflection points, find where the second derivative is 0 and undefined. Again, this is very similar to when we're finding if a function is increasing or decreasing, which you saw in a past lesson. So looking at this second derivative, it's not going to be undefined. I'll tell you that right now. There's no denominator here. And what we're going to do is then just set it equal to 0. So 0 equals 6x minus 6. Let's add that 6 over. Divide the 6, and we're getting x equals 1. Now, this is an inflection point. Okay? So if we want to jot that down right away, we can. So I just jotted it down over here to get it out of the way. Our point of inflection here in number 2 is 1. Well, the x value of our point of inflection, right? We're looking for the x coordinate of our inflection point. So now what we have to do is determine the concavity, right, here in step 2. So plug in values to the left and the right of your inflection points into the second derivative. Now this is key. You don't want to forget this. When we're doing this next part, and I'm going to walk through it for you guys, we are plugging in values back into the second derivative. It is the second derivative we're going to be plugging back values into. Now, this process, we're actually going to be using a number line here to help us determine our concavity. And I will say, I'm going to throw this notation here for the second derivative just to make sure that we are plugging these values into the second derivative again. I'm going to keep saying it because it's super important. We're plugging back into the second derivative. So what we're going to do here is set up this number line, kind of just looking at it at the x-axis. And what I'm going to do is plot my inflection point. And my inflection point here is 1. Okay, and I'm going to write this arrow just to help me out. And what my step 2 I wrote out is telling me to do is to plug in values to the left and the right of your inflection point. Okay, well, I'm going to pick 0, and I'm going to pick 2. Okay, so those are the two numbers we're going to plug into our second derivative. Now, you may be able to just do this on your calculator in your head, but for the sake of, just showing you computationally, let's just do it. So let's do 0 first. So 6 times 0 minus 6. Well, this is 0 minus 6. That gets me a negative number. Okay, and that means the interval, or to the left of our inflection point, we have concave down because it's negative. We get a negative number. So this is concave down, and I'm going to write that out, okay? And I want to go right back up here to relate it back to the steps I wrote out for you guys, is if the second derivative is less than 0, case A, it's concave down, right? We got the second derivative, it was negative or less than 0, okay? And that's why it's concave down over here. Likewise, let's plug in 2. Okay, so we have 6 times 2 minus 6, 12 minus 6. Well, that gets me a positive number. Okay, so my interval over here to the right of our inflection point is positive. That means I have concave up. Okay, so that's how we're going to be using this number line type thing to help us out and determine our concavity. Now, the last thing to do, right, is write our concavity in interval notation. And this is how we're going to do it. I'm going to split it into two separate statements. So concave up here, concave down here. And, well, let's just go left to right here on the number line. We have concave down. Well, that's going to be negative infinity to 1, right? And then our concave up is going to be 1 to positive infinity, right? So, and that inflection point is coming up in that interval, just like we were showing before in the picture at first. So this is great. This is our answer here for number 2. Okay. Now let's go into 3. Okay, let's keep going here. What we're going to do first, and I suggest you try it, get the second derivative of this function using the correct notation, right? F of x here. We get the second derivative to be 12x squared minus 4. Now make sure you get that, okay? Let's move into finding our inflection points now. Find where the second derivative is 0 in undefined. Well, it's not going to be undefined here. I'll say it right now, none of these are going to be undefined, okay? But what we want to do, right, is set it equal to 0 still, and find out where x is 0, so, or where the second derivative is 0, I'm sorry. And so what we're going to do is just add 4 over. So we get 4 equals 12x squared. We're going to divide by 12, right? Divide by 12. We get 1/3 equals x squared. Now, interesting thing happening here. To get x alone, we have to take that square root. Have to take that square root. Well, what happens? Square root rules. We know that this is going to be x equals positive or negative square root of 1/3. So what this is saying here is we have 2 inflection points, and our inflection points are negative square root of 1/3 and positive square root of 1/3. So we can jot those down right away. Let's just do it up here in the top right. So there they are, POI. That's the short change thing we're going to use, our notation here. And now what we want to do is determine our concavity. So let's do that. And this is where that number line comes into play. And make sure we're plugging back into the second derivative. Second derivative, we're going to plug in values to the left and the right of our inflection points, right? Because we have 2 here. Now let's plot those points, okay, on our line. So we plot our inflection points on the line here, and I'm going to write these arrows just to keep in mind those are my 2 inflection points. Now, our steps say, right, the steps we wrote out, or I had you guys write out if you did, plug in values to the left and the right of our inflection points. Well, let's plug in, let's just go with -1 here. Let's go with 0, and let's go with 1. Okay, those are going to be the easiest, I think. And again, we're plugging back into the second derivative. Now the second derivative is right here. Okay, so 12x squared minus 4. Now this is where I'm gonna refrain from going computational, doing this computationally, and just talking through it when plugging in the values. So we're gonna plug in -1 first into 12x squared. Well, a -1 squared turns positive, so 12 is still positive times 1. Minus 4 is still positive. So we're getting the second derivative is greater than 0. So this interval is positive, right? So that means we have concave up here. Now let's plug in 0. Well, 0 squared is still 0. Times 12 is still 0. Minus 4, well, that's a negative number. So the second derivative is less than 0. Okay, again, it says right here in these steps, this is a case A here in this interval. The second derivative is less than 0. That means we have concave up in this interval. Or, sorry, concave down. Excuse me. Concave down. And then let's plug in 1. So 12x squared, well, 1 squared is 1 times 12 is 12 minus 4, and that's still positive. Okay, so this interval, we're still positive here, which means we're concave up. Now, again, last step to do, write out our intervals in interval notation. And I'm going to just move our POI, our points of inflections, down here and write our interval notation down here as well. So let's do that. And here we are. So negative infinity, right? As far as we can go left, this interval, negative infinity all the way to negative square root of 1/3, our inflection point, is concave up, and we determined that. Same with here, I wrote the concave up next to each other is the square root of 1/3 to positive infinity, right, forever going to the right. And then that middle interval is where it's concave down. So negative square root of 1/3 to positive square root of 1/3 is that interval where it's concave down. Okay, so that's how we would write it. This is our final answer, and boom. So there's number 3. We're getting there. We're getting there. Let's move on to number 4 here. I already got my number line out. Okay, definitely try this one on your own. Pause if you can do it. Let's go straight into the second derivative, just like we've done in these last 3. So let's do that. Keeping in mind our notation, right? It's y equals, so we're gonna write the d squared y over dx squared. So let's do that. And there's our second derivative. Hopefully you got that, so check that out. 20x cubed minus 12x. Okay. So now let's determine our inflection points. Again, we're going to be finding where the second derivative is equal to 0 and where it is undefined. Well, it's not going to be undefined here, so let's just set it equal to 0 now. Where is our function, the second derivative, equal to 0? Well, we got to do a little bit of algebra here to find x. So what I think I'm going to do here is take out 4x here first as a GCF, and we get 5x squared minus 3, okay? Now 0 equals 4x. Well, x equals 0, okay? That is an inflection point, or a point of inflection. I always say inflection point. None of the matter. But, and then we also have to set this other piece to 0. So 5x squared minus 3. Now we're going to add 3 over, and I'm running out of room here a little bit, but we're going to divide by 5, right? So we're going to get x squared equals 3/5. Now, again, we still have to take that square root. So this is really, really similar to our last problem, okay? And we're getting, where should I write this? X equals positive or negative 3/5. Square root of 3/5, okay? So there's another inflection point. Points, I guess, 2 more. Sorry, positive and negative. There's 2 more there. So this is really similar to number 3. Instead of 2 inflection points like in number 3, we have 3 now. We have x equals 0, and then we have plus or minus the square root of 3/5. Okay, so what we can do is jot those POIs down. So there's my POIs. Now our next step is to determine this concavity, okay? And again, we're plugging values to the left and the right of our inflection points into the second derivative. The second derivative, okay? And I'm emphasizing that again. Our second derivative is right here, okay? So that's where we're plugging in. Let's get our inflection points on our line. So there's our POIs on our graph. Now let's choose values to the left and the right of those points of inflection that we're going to plug into our second derivative, right? We're just following that step 2 in our steps. And let's pick -1. That's going to be easy. In between these 2 inflection points, let's do -1/2. Now, yes, -1/2 is in between these 2. If you need an approximation of the square root of 3/5, it's around 0.77, so -0.77, which is less than -1/2, so it is in between there in 0. So likewise for this one, it's going to be +1/2. And then out here, let's use just 1. Okay, so we have 4 values now we're plugging in to our second derivative. Now, I'm not going to write this computationally again. Let's just talk through it, okay? You definitely can go ahead and write it computationally if that helps you, okay? Otherwise, let's just talk through this. And -1 cubed, I'm looking at, sorry, I'm doing this one first. -1 first. -1 cubed is still -1. Times 20 is still -20, okay? Minus 12 times -1, well, that's going to turn into +12, but we have -20 plus 12 is still a negative number. Okay, so that's less than 0. That means we have a negative, or we're concave down, right? We're concave down. The second derivative at -1 is less than 0, therefore concave down, right? And we can just refer back to those steps, right? The second derivative less than 0. let's plug in negative 1/2. Now, negative 1/2 cubed is really negative 1/8. 20 over negative 1/8 is 20 over 8, which is roughly, let's do it in our calculator here, so negative 2.5, and then we have to do plus 6, right? Because 12 times 1/2 is 6, so plus 6, well, that's going to be positive. Okay, so we have positive here in this interval, so we're concave up. All right. Let's do 1/2. Well, 1/2 cubed is still 1/8. 20 times 1/8 is 20 over 8. That's positive. What is that? 2.5. And then minus 6, though, that's going to get us a negative number, so we're less than 0 there. So we're negative here. And that means we're concave down. Okay, and we have one more interval to go here, and it's where it's 1. So 21 cubed, well, sorry, 1 cubed times 20 is still 20, minus 12, well, that's still positive. So we're positive out here in this last interval, which means we're concave up. So we have where our function we have our function's concavity now, and now the last thing we need to do is just write it in interval notation. And there they are. So I listed concave up first. It's negative square root of 3/5 to 0, okay, which is right here in this interval. And then square root of 3/5 positive infinity, right? So from this inflection point on, forever to the right, or infinite to the right. And then concave down, negative infinity to negative square root of 3/5. Okay, so that first interval we found. And then this third interval we found 0 to the square root of 3/5. Okay, so this is our answer. Hopefully that's clear, and we can box that up for our answer. Now let's move to 5. Okay, and it's going to be the same steps, right? Same exact steps. Let's find that second derivative first in our inflection points. So there's our second derivative. Make sure you check that out, 6x minus 12. Now let's get our inflection points. So 0 equals 6x minus 12. This one looks pretty nice, right? We're going to add 12 over 6x, we're going to divide by 6, so x equals 2 here. That's our only point of inflection here, is x equals 2. And I'm just going to underline that in purple. And now, let's determine our concavity. Okay, so let's plot that point of inflection on our graph, right? This is our point of inflection. And we're going to pick values to the left of that and to the right of that to plug back into our second derivative, right? This is our second derivative. We're plugging those values back into the second derivative. So let's pick 1, let's pick 3. Okay, those are going to be the easiest here. Well, 1 times 6, and you could probably do this one computationally if you wanted. 6 times 1 is 6, minus 12 is negative. So we're negative in this interval, which means we're concave down, okay? And then 3, well, 6 times 3 is 18, minus 12 is still positive. We're positive in this interval, okay? So that means we're concave up, all right? And then our last step is to write our POI, our points of inflection, which is just 2 here, and then our intervals in interval notation. So concave down, we're negative infinity to 2, and concave up, we're 2 to positive infinity. Okay, so this one was nice and quick. Really nice when you only have one inflection point. That makes a huge difference, right? It gets a little more complicated when we have more than one point of inflection. So let's move into our last problem. Again, same thing we were just doing. We're going to find that second derivative first. So let's do that. Keeping in mind our notation, right? Right here we have the y, so we're going to be using that dy dx. So let's write that out. So there's our second derivative. Make sure you check it out. Make sure you got the same one, 12x squared minus 6x minus 8. Now, our next step, where is the second derivative equal to 0 and where is it undefined? Well, it's not going to be undefined here. But what you may be thinking is, and if you already tried it, is how am I supposed to get x here? How am I supposed to get my inflection point when this second derivative actually is not factorable? Oh boy, not factorable. So what that means is we're going to have to use something else. Now, that something else is the quadratic formula. Okay, so we're going to be using the quadratic formula to find out where the second derivative is equal to 0. Well, I hope you remember the quadratic formula because we have to use it. Now, if you don't remember, here it is. This is the quadratic formula, okay? Now, let's plug in our values from the second derivative into that formula. So there you have it. And what I want to do is just get it to a point where we can type it into our calculator to get that x value. So let's just simplify this a little bit. And I'm just going to do it live here. And what I'm going to do is just change the signs here. So negative and a negative is just positive. Plus or minus now, under the square root, I'm going to do 36. And if you multiply the 4, the 12, and the negative 8 out, you're going to get 384, and 36 plus that 384 is going to be 420. And let's just keep going here. I forgot to plug in the a here. This a, right, is 12. So that should be a 12 there, which means we have 24 in the denominator. Okay, and then one last step would just be writing 420 under the square root sign. Now, again, because we have this plus or minus sign, we're getting two values for x. So the way I have my algebra students do it is really just split the equation into two. You can write it into two. Maybe you don't have to. You can just do it in your head and in your calculator. But you would split it like this. So computationally, if you want to write it this way, and it helps you, then do that. Okay, so I'm accounting for the positive square root of 420 and the negative square root of 420 there. Well, you should get x to be positive 1.1 and negative 0.6. Now, these are our inflection points. Okay, so we have to put those onto our number line when we're determining concavity. So let's do that. And I'm just going to adjust my number line a little bit here. Let's throw on our inflection points. So it's negative 0.6 and 1.1. Okay, now we have to determine, or we have to plug in values to the left and the right of those inflection points into our second derivative, right? This guy, and it's right there. Okay, let's use negative 1, 0, and 1, just the easiest ones that are going to be able to, evaluate easier. And you know what? I do like writing these arrows here to show that these are our inflection points, just to remind ourselves. Now let's plug in negative 1 to our second derivative. Well, negative 1 squared is positive 1 times 12 is still 12, minus a 6 times a negative 1, which would be plus 6, which is 18, minus 8 is 10. Well, we're still positive there. We're still greater than 0. Our second derivative is greater than 0 there. So we're concave up here. Concave up. Okay. And you know what? I probably want to use a different color there. Let's do blue to show our concavity. And so we were positive here, and then concave up. Let's plug in 0. 0 squared is 0, times 12 is 0, minus 6 times 0 is 0, minus 8 is negative. Okay, so we're negative in this interval. That means we're concave down. Again, you can always write this out computationally if you want to plug in these values, right? Negative 1, 0, and 1. But I'm just doing it in my head and on my calculator to go quick here. Now, last one to do is plug in 1. Well, 1 squared is 1 times 12 is 12, minus 6 times 1 is 6, minus 8. Looks like to me we're getting a negative value there. Okay, definitely not. It's 12 times 1 squared, which is 12, minus 6, which is 6, minus 8, that's negative 2. So, wait. Would you look at that? Why are we plugging in 1 when that's not greater than 1.1? So what I'm going to do here is just adjust what we're plugging in here. You probably caught that sooner than me. what we're going to plug in is 2 here. Let's plug in 2. So 2 squared is 4 times 12 is 48. Minus 12, 36 minus 8. Well, that's 28. We're still positive here. So positive here. Sorry about that. Hopefully you caught that. That's totally my fault there. Prone to mistakes when we're going fast. I know I don't want to keep you too long. But there we are. There's our 3 intervals. Now our last job is writing it all formally. So here's my POI. We get negative 0.6 and 1.1. And then our interval notation is concave up negative infinity to negative 0.6, our first inflection point. And then 1.1 to positive infinity, or concave up, right, this interval. And then concave down negative 0.6 to 1.1, which was that middle interval here. So there we have it. We got through them all. Hopefully this is making sense to you guys. Again, always fall back on these steps if necessary. Okay, and make sure we're plugging back into the second derivative. I want to keep saying that just because it's so important. Sometimes students will go back into the first derivative or back into the original equation when it's not. It's the second derivative. Okay, and we wrote that next to our number line here each time. So hopefully that went all right for you guys. Again, if you have questions, I'm here. Miss Vasquez here. Miss Weedoff. We're all here for you guys. Ask away. Always feel free to pause, rewind, fast forward, whatever you need to do. But that's it for day in 11.4. Hope to see you guys soon. Talk to you guys soon, and we'll see ya. Thanks.